Hello and welcome to this part of the tutorial. In this part I will actually show you how to analyze parallel execution skew without having a diagnostic or tuning pack license. And while doing so I will point out what kind of shortcomings this approach has. So for analyzing parallel execution skew, having a diagnostic pack license and a tuning pack license is quite helpful, and it allows a quite sophisticated kind of approach and analysis that is not possible without having diagnostic and tuning pack license. So as I pointed out in the introduction, for a systematic approach analyzing parallel execution skew, there are two questions to address. The first question is to find out whether a parallel SQL execution was affected by parallel execution skew, and in particular to what degree it was affected by parallel execution skew, because one important point in my opinion is that not all parallel execution skews are the same in terms of to what degree they affect the overall execution time. So you might have a skew in work distribution that has a significant impact on the overall execution time, whereas you might have a parallel execution skew that has just a very minor impact and really doesn't matter for the overall execution. So ideally we would have some kind of measure that tells us do we really have a problem with parallel execution skew, or is it something that we can simply ignore or that we simply do not have? But even if we have it, to what degree does it affect the overall execution? So that is, in my opinion, the first thing that needs to be clarified. And the second question is then, if we have a problem with parallel execution skew that is worth to deal with, how do we identify the problem on execution plan line level? Because only if we know on execution plan line level where the data distribution problem, for example, happens, then we are able to use a systematic approach to address the problem, rather than trying with trial and error and playing around, which is kind of an unsystematic approach. So for a systematic approach, we first need to find out, do we have a problem with parallel execution skew, and if yes, identify the problem on execution plan line level so that we understand what measures we might have to take in order to address the skew problem. So the first thing that I said is, how do I find out whether a SQL execution is affected by parallel execution skew or not? And ideally I would like to have this measure, this analysis done without any further overhead. So I would like to have this without having to reproduce the problem. So ideally I would like to be able to press a button when I come in on Monday and I have a large batch job that ran over the weekend, and someone says it took 3 times longer than usually, and you know that it's basically the batch job consists of a large parallel execution. Then for this past execution, ideally I would like to be able to press a button and find out was parallel execution skew a significant contributor to this long execution time, or it wasn't. So that is the ideal way of answering this question that I have in mind, and that would be great if we could do this so that we do not have to dig out the actual execution, the SQL, then try to reproduce it, then in order to find out whether we had a problem with parallel execution skew or not. Imagine you no longer have the data that might have been loaded over the weekend, or it simply takes hours to reproduce. You might have other jobs that are running concurrently already on Monday that you do not want to disturb by running an additional job that was supposed to run over the weekend, and so on and so on. So ideally I would like to be able to answer this question without these additional steps. And unfortunately, without having the diagnostics pack license, this is, as far as I know, not really possible. As we will see later, you might be able to instrument your code in a certain way that you basically lock additional information that can tell you information about parallel execution skew. So that might be one way that you have your application instrumented in a certain way. But as we will see, this approach is unfortunately pretty limited, comes with many an awful lot of restrictions, and is therefore not really that applicable as a general approach. It might be helpful depending on what kind of parallel execution you perform, and this has to do with this shape of the parallel execution plan, what I explained in the previous part of this tutorial. When you start having multiple DFO trees, or if you use certain constructs, then this approach that I will show has a lot of restrictions that unfortunately haven't been addressed yet, even in the latest version, even in 12.1. This is not this didn't get any better, but I will show that in a moment. So what can you do if you do not have a diagnostic pack license to get in close to this ideal description that I've just used? Well, in my opinion, if you do not have a diagnostic pack license, then the best thing that you can do is getting SASH installed on your system, which is the free version of Active Session History, which was initially done by Kyle Haley and is now maintained on I think on SourceForge by Marcin Piorowski. I don't know whether I spelled I pronounced his name correctly. Another fellow from the Oak Table who is maintaining SASH, and it's basically the free version of Active Session History, because Active Session History is, in my opinion, the best way to answer this initial question whether an execution is affected by parallel execution skew or not. The good thing is that if you have this free version of Active Session History installed, then you can, for instance, use this so-called Ash viewer, which is also free, which allows you a graphical analysis of your data collected, this Active Session History data. And also my Xplan Ash tool here is capable of working together with SASH. So ideally what you want to see for SQL execution to understand whether it's affected by parallel execution skew or not is a graph like this one here. This is the so-called activity tab from the real-time SQL monitoring. But in order to have that, you have to have both. You have to have a diagnostic and a tuning pack license. Otherwise, you are not allowed to use real-time SQL monitoring information. So that is basically the nicest way how you can look at that information. And what you see here is that we have this particular degree of parallelism, and if your parallel execution is not affected by skew, then it's supposed to look like this. Ideally, you want to have this level of activity here for most of the time, at least at the degree of parallelism. So this one here ran at a degree of 8, so for most of the time at least 8 parallel execution servers should be active. Then it's very sure that you do not have a problem with parallel execution skew. Why at least? Why can you have more than 8 or more than the degree of parallelism active servers concurrently? Simply due to this consumer-producer approach, where you have 2 sets active, so you can end up with actually more than the degree of parallelism active servers concurrently, up to 2 times, and if we think about these multiple DFO trees, then you can have even more servers in theory active. But for a single DFO tree that runs at a degree of 8, for example, you should not see more than 16 at most parallel execution servers active. But typically you would see something around the degree of parallelism ideally. So this here, this is what you want this to look like, that you have for most of the time your parallel execution servers at least active, with a number of active servers close to the degree or maybe even higher. And this here is usually a clear sign of a problem with parallel execution skew. So for a significant amount of time of the execution, you had only a few parallel execution servers actually involved that were working actively, and the others were idling around. So this is the best way to understand whether parallel execution skew is significant or not. As I will show you in the next part of this tutorial, where I will deal with the diagnostic and tuning pack way of analyzing parallel execution skew, we will see that this real-time signal monitoring information is not always telling you the truth, so you have to be careful here. But in general, this is the way you want to look at the information, and this has also the nice advantage that it's available for past executions. So if it's not too long ago, because the real-time signal monitoring information ages out of the memory after a while on a busy system, this can be rather soon. But if it's not too long ago, then even if the SQL execution is already in the past, you can get this report still, or you might even instrument your code to write this, to archive this report somewhere. And I think in 12c there is actually some way that real-time signal monitoring reports will be archived by Oracle automatically. But basically, that's the way you want to see, you want to look at whether you have a problem that is really important in terms of parallel execution skew, or whether it can be ignored. And as I said, this is not that easily possible without having diagnostic pack license. The funny thing is that this part here actually is coming, this information is from the real-time signal monitoring report, is solely covered by active session history. So the only source for this information here is active session history. So you don't need actually a tuning pack license to extract this information, but you need a tuning pack license to get a real-time signal monitoring report. But that's just another detail. So my point here is, if you do not have a diagnostic or tuning pack license, you cannot get this, which would be the best way, because it doesn't come with any overhead. It can be done for past executions. And it's a very nice way of understanding whether you have a problem with parallel execution skew, and if it's a significant problem with parallel execution skew that it's worth to address, so that if you address it, that you will really gain something in terms of much quicker execution times. So if you do not have a diagnostic pack license, if you install SASH, then you can use my XPLAN-ASH tool. And XPLAN-ASH will be able to extract this information here from SASH, which is exactly this crucial information that tells you about the average activity. So that is basically the same graph that you saw here. This corresponds to that. If you have a bit of fantasy, you can see that this is basically the same graph, just in a different representation, so that we see here the time and we see here the activity. We see the difference between CPU and non-CPU activity, that is this asterisk and then the star, what is represented here, and it more or less corresponds to what you see here. So XPLAN-ASH can give you this information from SASH without a diagnostic or tuning pack license, and you can, using XPLAN-ASH and SASH, you can answer this question for past executions without any overhead, well, at least a small overhead of collecting the data using SASH. But it's, in my opinion, the most suitable and nicest way of trying to find out whether you have a problem with parallel execution skew or not that is worth to tackle. Yeah, so that is this first question that you need to address, whether you have a problem with parallel execution skew and for that specific SQL execution or not. That is the most important one, because if you do not have a problem with parallel execution skew, or you might have a problem with parallel execution skew that is simply not worth the effort, because maybe your execution is just affected for, let's say, 10 seconds, but the overall execution time is 10 minutes, then the most you can gain by addressing the parallel execution skew would be these 10 seconds. So very likely, if you want to reduce the 10 minutes overall execution time, you have to focus on different things rather than dealing with this parallel execution skew. That is, in my opinion, a very important point to differentiate for a systematic approach. And in my eyes, you can only in my opinion, you can only see this via this active session history information. And if you do not have a diagnostic pack license, then I recommend to use SASH, because explain-ash is then capable for a SQL execution to extract this information. And you get it basically also for past executions, which is also very important without having to reproduce the issue. Right, so that is the question whether you have a problem that is about parallel execution skew or not. Then, if you have a problem with parallel execution skew, the next step is trying to understand on execution plan line level where the skew happens and what you can do about this. And this is the area where you can make use of a rather special view in Oracle that is called VPQ-TQ stat. And this view is basically only populated in the private memory of the query coordinator session after a successful completion of a parallel execution. So that is already a very important point to understand. You can't query that information from a different session, so it can only query that information within the query coordinator session that just successfully executed a parallel execution. So if, for example, your parallel execution gets cancelled, or if your parallel execution runs into an error, typically running out of temp space, then this view won't be populated. So this information is only available when you successfully complete an execution, which is in particular a pity if you try to reproduce the problem and you're not really interested in running a 10-hour batch job again, only to see the parallel execution skew problem. If you maybe would be able to identify the problem already after 10 or 15 minutes, if you cancel it and then try to query this view, you won't get any information. So that's quite a restriction and quite a limitation that can, that doesn't make life easier. But unfortunately, there are even more limitations with that approach, as I will show you. So yeah, so you can use this special view under these circumstances that you ran successfully to completion, and then this view will tell you about the data distribution for each of these table queues that were used as part of your execution plan to redistribute the data. So as I've shown you in the previous part of the tutorial, if you have a parent-child data flow operation that talks to each other via these table queues to redistribute the data, then for each of these table queues the $PQTQ stat view is supposed to show you how the data was actually flowing through these table queues. And this would then typically look like this here. This is a parallel execution that I've used here to demonstrate this, and this actually is the parallel execution that led to this activity here. So this is one that is obviously rather significantly affected by parallel execution skew. And if I run in the session that ran this parallel execution, if I run now this query on $PQTQ stat, and I use a slightly improved query, let's say, that does some graphical representation of the information, so it tries to give it a bit better reading so that you get a better idea of what this view is trying to tell you, then we get a result like this here. So how does this work with this view? We have here this table queue ID information, and this table queue ID information is basically how you can link your information that is shown here in the view, this output, how you can link it back to the execution plan. For example, this table queue ID 0 then corresponds to this redistribution that happens at this stage here. So we can see that these 2000 rows were distributed by this producer set of parallel execution servers, and we see here the number of rows that each parallel execution servers produced, and we see here the number of rows that each consumer parallel execution server in the other set, in this case in this set that is running this DFO number 4, how it received this data. And we can see here the difference between the producing part and the consuming part. By applying this hash function, the data was differently consumed than it was produced. That's the way this hash distribution works, so that the rows get distributed from one parallel execution server in this set here to one of the parallel execution servers in this set here. So we see that we in total have produced 2000 rows and we have 2000 rows consumed. And this graph here is just an addition that I've added so that you can get a bit of a graphical representation how even the distribution was. And we can see here that for this very small table, running it in parallel, which isn't really that sensible for 2000 rows, running it in parallel, and we can see that running parallel on such a small table then also doesn't bring you that even distribution on the producer side, because these row ID ranges that each parallel execution server runs, these block granules that are determined very obviously didn't really lead to a very even distribution. But on the consumer side we see that the hash distribution was working pretty well, so that we have a rather even distribution on the consumer side. So, and that is basically, you see now this information repeated for each of these table queues. So we hear this, see the next one is this queue number 1 that talks to the same, that is the DFO number 1 again talking to DFO number 4, distributing T2, the full table scan of T2 by hash again. And now we see also that the full table scan was quite okay in the what the distribution of work was okay in that part, and the hash distribution was yeah, well, not that even, but also not that I think not that bad. Yeah, and you see here if you run at a certain degree and you have a certain number of table queues, then this is quite a lot of output that you get. That's the first thing. So if you do not use this kind of nicer formatting of the output, then you can easily get lost in the number of rows that are returned by $PQTQstat. But the good thing is here, at least with this, in this case here, it's rather obvious that we have for this table queue number 7 here, we have for the table queue number 7, we have identified that we clearly have a skew problem here. So we see that we have a quite even distribution on the producer side. So let's see that in the execution plan. It's about this here. Here something bad happens. So this DFO number 7 obviously has still a very good distribution when sending this data here. This is what we can see here confirmed in the upper part, but in the lower part, the consumer part, this DFO number 8 here that receives the data at this stage, clearly now something bad happens, because all these 666,000 rows are actually coming to the same parallel execution server, and this poor guy now has to do all the work, and all others are then more or less idle. So here we can by using this view, we can clearly identify the skew problem that is happening. So that's a good thing. We have now identified on execution plan line level where the problem happens. And of course, for a complex parallel execution plan, you might have multiple of such cases. So you're not necessarily limited to one skew problem. You could have multiple distributions that go wrong. And but in order to understand what you can do in order to address the problem, this is the crucial information that you can see that is obviously somehow related to this join here, to this hash join that is happening here. Something about the distribution, the hash distribution, which is based here on the join keys, is going wrong. And therefore, if we look at this operation here, this operation number 6, then we would know that one of these expressions here, or this join expression here, somehow leads to skew, and this is the thing that we would have to then think about how and if and how we can address this skew that is happening here. And this is exactly what I cover in this allthingsoracle.com mini-series, where I show you, if you have a parallel execution skew problem, ways how you can address the problem. Therefore, I won't go into that here in this tutorial. Here we are just dealing with how we can identify the parallel, how we can analyze the parallel execution skew problem. Now, having said that, I will show you now a different parallel execution and the output from $PQTQstat. This is this one here, and in this case here we see, if we look at the output from $PQTQstat, we can again identify that we obviously have a quite significant skew here happening for this table Q number 1 in this case. But the problem is, and that's what I tried to express with my initial question that I would like to answer first before looking at this $PQTQstat output, is, do I really have a problem with parallel execution skew or not? Although you see here quite a significant skew in the output from the view, if we look at this picture that is not available to us without a diagnostic and tuning pack license, at least not if we're not using SASH and XPLAN-ASH, you will see here this is the picture, and obviously dealing with this skew here won't buy you much, simply because there is not much of a skew. There is no significant time that you can see where less workers were active. So we see here at the beginning, maybe you could address this very short period of time where obviously not all of the parallel execution servers were active. Then we might have this short period here. But apart from that, for the majority of time, the parallel execution servers were actually quite busy. So that's my point. If you see skew confirmed by $PQTQstat, it doesn't tell you anything about the significance of this skew. So that's my point why I want to address the first question. Is this skew, is there skew, and in particular, is the skew significant? Because by simply looking at the output from $PQstat, this looks quite significant. Here in this area, we have a significant skew, but for this execution, it simply isn't really worth to deal with, because I cannot really save a lot of execution time because my parallel execution servers are busy anyway. So that is a part that is simply something that you cannot tell from looking at PQTQstat. How significant is the skew, if there is any skew? Yeah, and that's why I recommend, if you run parallel execution without diagnostic tuning pack license, get SASH installed and use XPLAN-ASH. Then you will get this graph here from XPLAN-ASH, and it will tell you whether you have a problem with parallel execution skew or not. You can check whether I have this output available. Yeah, this is the one. So this is what you would get from XPLAN-ASH, so that you see here this corresponding output that you see confirmed that you're running at a degree of 8, and for most of the time you are actually running at a quite good work distribution. So the skew is not really relevant in this case here. Right, so that is the way you can try to get an idea of addressing the first question, and addressing the second question you would use this $PQTQstat. Now, I've already said the problem with this view is you cannot query it from outside. So if you want to be able to see the view contents without having to reproduce the issue, you would have to instrument your application that after each parallel execution you actually somewhere log this output from $PQTQstat, right? Because you have to query it from within the query coordinator session. And yeah, that's something that is obviously not always possible if you, for instance, have some reporting tool or something like that that's simply not capable of probably not capable of running that additional code. Maybe you can add some individual code to the reporting tool, but as I said, you have to somehow add it. You have to instrument your SQL executions. Now, the bad thing about $PQTQstat is that it doesn't work very well. It simply is the case that it misses some. The code that populates the view simply hasn't been updated properly. So new features that get used, the code that deals with $PQstat that populates the view obviously doesn't cope very well with some SQL features that get used. For example, I have here the same query again that has this skew problem that I've shown you, which results in this activity pattern, but I have rewritten it just to use a temp table transformation. So it's semantically the same statement, it results in the same problem, and it does achieve the same result, but it uses a temp table, a parallel temp table transformation. And that's one of the downsides of this $P-Q-T-Q stat thing. You see here the view simply doesn't return any useful information. There's just a table Q0 mentioned, and all the other table Qs that you see in this output, which should actually be there, are missing from the output. So parallel temp table transformations are one of the constructs that obviously make $P-Q stat break. So that's a bad thing. So even if you instrument your code, you might have a lot of SQL executions, depending on what you do, where you do not get any useful information from $P-Q-T-Q stat. That's bad. And it hasn't changed in 12c either, so you still have the same limitations. Then another thing which is quite irritating with P-Q stat, I have here one of the examples from the previous tutorial. That is the one which has multiple DFO trees. So if you happen to have multiple DFO trees, then in many cases P-Q-T-Q stat returns something that looks like reasonable output. So there is output, but unfortunately the output is completely misleading, in fact is a complete mess, so doesn't have much to do with the actual activity. In this case here, we have this different DFO number. In this case it's not a DFO but a DFO tree. But this is what this means. So we have several DFO trees covered in the P-Q-T-Q stat output, DFO tree 1, 2 and 3. And we have also here consumer producer information about these table queues. But if I look at the actual corresponding execution plan, and I have to find it here in my output. So it took me a while to find it. So this is the corresponding execution plan, and let's have now a look at the output from P-Q stat. We start at a data flow tree. We start at a DFO tree number 1, which is, according to the execution plan, this part here. This is DFO tree number 1, which is just a full table scan of T2 at a degree of 4 according to the real-time SQL monitoring information. And we see here P08, 9, 10 and 11 were involved in this operation. And we can also see, since this is a DFO tree with just a single DFO, we expect just a single set, so no redistribution necessary. So let me repeat it again. DFO number 1. Let me repeat it again. DFO tree number 1 at a degree of 4, no redistribution, so a single set with P08 up to P011 involved in the operation. That is what we can see here from the execution plan. Now have a look at DFO tree number 1. We see here a table Q 0, 1 and 2. And we see processes P004 to 7 and P0 to 3 that are involved. Clearly, these two things do not fit together, because there is no table Q 1 and 2 in DFO tree number 1. And also the processes do not fit, because according to real-time SQL monitoring, we had here this processes involved, 8 to 11, that were doing this full table scan here. And we see here TQ ID, table Q IDs 0, 1 and 2 and different processes. Very obviously one of the two is incorrect, and I'm pretty sure that real-time signal monitoring information in this case is more reliable than this information here. Then let's look at DFO tree number 2. DFO tree number 2 is this one here, running at a degree of 8, and the processes that were involved are obviously 12 to 19, I would say. Let's have a look at the different location here of the output. So that's 12 to 19. Again, we have a single set because we do not have a redistribution. We have a single DFO that is making this DFO tree. Let's have a look. And we see here this. We see here this output. This is DFO tree number 2. And we see here a quite confusing output again. The query coordinator is now part of the producer part, and in total we would distribute 1.3 million rows. And we have here these processes involved. So you see, this is more or less pointless and quite confusing, this output, because it doesn't seem to have much to do with the actual activity. And that's then of course again a pity that VDOLA-PQ-TQ-STAT produces such a nonsense. So at first glance it looks like a reasonable output, and only when you start to look more closely at it you realize that it's just a complete mess. Yeah, so that's quite another limitation of VDOLA-PQ-TQ-STAT, which doesn't really help for more complex execution plans, that it does produce that misleading stuff. I mean, in this case here, it's very obvious from the output, if you look at it, that probably it doesn't correspond to what the actual activity is. But this case here looks somehow like something that might be reasonable, but in fact it's not. And then finally, if you deal with full partition-wise operations, which operate at a different granule level, because we in this case use then partition granules instead of block granules, so each parallel execution server is working on a partition level rather than on a row ID range level. In this case here, again you have the problem, since a full partition-wise operation doesn't have to redistribute data because the data is already partitioned in a suitable way, so data doesn't need to be redistributed. That's one of the beauties of a full partition-wise operation. Then again, the view isn't really helpful if you look here at the output, since we do not have any redistribution, and VDOLA-PQ-TQ-STAT is only about table queues, part of a redistribution. For analyzing a full partition-wise operation, again, the view is completely useless because it doesn't tell you anything about the distribution of data on partition level. So if you use full partition-wise joins, for example, then you cannot tell whether you have a problem with partition skew, because of course you can have with a bad design, or if you're unlucky, something bad happens, then you can end up with an uneven distribution of data on partition level, and then VDOLA-PQ-STAT at least doesn't tell you anything. You might be able to tell it from the statistics on your partition level, but you won't be able to tell it from the runtime statistics that VDOLA-PQ-TQ-STAT produces. And we can have a look at explain-ash, for example, in such a case. Which is this execution plan here. And it becomes very obvious from the information that you get based on the active session history that we really have a significant problem here with skew, and for most of the time actually run on a single parallel execution server, simply because the partitions are not containing the same amount of data, which we can see confirmed here from the real-time SQL monitoring information, which is something that Explain-Ash also can extract. If you have this license, if you use Sash, you won't get that information. So if you do not have a tuning pack license, or if you don't have a diagnostic pack license, then this information on that execution plan line level cannot be extracted. So that is another problem, another limitation of this approach, that you can't really analyze full partition-wise operations. Right, so are there any other ways you can use to maybe overcome some of these quite significant limitations of this approach? Well, one other way that you can use, and that is not limited the way that $PQ, the view $PQ stat is limited, that is using extended SQL trace, the good old tracing. But then you have another problem. If you use extended SQL trace, then again, of course, you have very likely the problem that you first have to reproduce the problem. With $PQ stat, you at least have the problem that you might have to reproduce it, or if you instrument your application accordingly, you might even get that information from some log information that you log away during execution. With extended SQL trace, this is very likely that you do not have it enabled by default, so it requires to reproduce, and you have of course the problem that extended SQL trace comes with overhead. So that's two problems of that approach. Then another problem of that approach is that you have unfortunately the problem that you end up with trace files per parallel execution server. So for instance, here running at a degree of 32 or 64 in this case even, then you end up with dozens of trace files that need to be analyzed, and there is simply no tool that I know of that does a reasonable analysis of parallel execution using extended SQL trace. I've used here this TRCA trace analyzer that is available from Oracle support, that is actually capable of dealing with multiple trace files. So you can give it a bunch of trace files, a list of trace files, but it also fails in cases where you have, for instance, a cross-instance parallel execution. So if you have rack and you have multiple instances involved, then this tool here won't be able to collect the trace files from the multiple different nodes. So that's another complication that you have with extended SQL trace. If in case of rack and cross-instance parallel execution, you really have then to deal with trace files that get generated on different instances. So that's really not really that easy to handle then. And then the next problem is that in order to get a good picture of the information that is buried in this trace file, I'm not aware of any tool that does a reasonable analysis. For example, if I want to find out about parallel execution skew, I get here the actual cardinality on row source level in the trace files, but you can see that TRCA gives me then as many copies of these row source statistics as there are trace files. So I have to wade through each and every output and see whether I can identify here in that output that I have a problem with parallel execution skew. Here in this case, maybe we can spot this here. I have 0 rows in that parallel execution server and 2 million rows in another parallel execution server. So I might be able to spot it, but very likely you would have to write your own tool to automate this, because you probably do not want to wade through dozens of these copies manually and try to find the problem yourself. So that is a rather cumbersome approach, and at least I'm not aware of a tool that does this automatically on trace file level. So you would have to come up with something your own that helps you to dig these trace files. So the good thing of this approach is it doesn't have these limitations with temp table transformation and multiple DFO trees and what have you, all these things that break the $PQTQ stat output, but it has other problems. So that's also not really a helpful approach. And also it doesn't help you with answering this first question, this thing, do I really have a problem that is worth dealing with parallel execution skew or not? It's also something that I believe you cannot really tell very well from an extended SQL trace. And then finally there's DBMS Xplan display cursor, and I've blogged here about that quite a while ago, where I've shown some limitations of display cursor. If you use parallel execution, then it doesn't really help you much, simply due to these things. If you have a cross-instance parallel execution, or if you have multiple DFO trees with different child cursors, all these things are things that the display cursor doesn't really cope with very well. And in terms of parallel execution skew, it doesn't help you at all, because it doesn't show you the cardinalities on server parallel execution server level. You get only a summary, if at all, which doesn't really tell you how the time and the work was distributed across the involved parallel execution servers. So display cursor is not really helpful for either of these two questions. So yeah, you're left with $PQTQ stat. It's rather harsh restrictions, and extended SQL trace with rather tedious, cumbersome handling, and therefore I recommend for those don't having a diagnostic or tuning pack license, get SASH and Xplan to address the first question, do you really have a problem with parallel execution skew that is worth to pursue? And for answering the second question, well, I would say ideally instrument your application that you somehow manage to lock away the output from $PQTQ stat, but then you are left with all those cases that are not properly covered by this output, and depending on what you do, these might be a lot, and therefore yeah, you just have then the problem that for some cases it's not that easy to troubleshoot if you have a parallel execution skew problem where the problem in the execution plan is. So can we do better? Yes, we can do better if we are using diagnostic and tuning pack license, and that will be part of the next tutorial that I will publish.